So we are going to talk about what is normal. All right, so we've talked about the uh, symmetric distribution already in the previous lessons. Now we're looking at calling this a normal distribution. It is symmetric. It has a bell-shaped distribution. It has a single peak, so a single mode. The peak corresponds to the mean, the median, and the mode, because remember we talked before that if it's symmetric, the mean, median, and mode are equal. The variation of the distribution can be characterized by its standard deviation, and the total area under the curve, no matter how the curve looks, is going to be equal to 1. All right, so the total area under this curve will be equal to 1. All right, so there's some conditions for normal distribution. A data set that satisfies the following 4 criteria is likely to have a nearly normal distribution. First one, most data values are clustered near the mean, giving the distribution that well-defined single peak. The data values are spread evenly around the mean, making the distribution symmetric. The larger deviations from the mean become increasingly rare, producing the tapering tails on the side. And individual data values result from a combination of many different factors, such as genetic and environmental factors. All right, so is it a normal distribution? So which of the following variables would you expect to have a normal or clearly normal distribution? Scores on a very easy test. Do we think that that would be a normal distribution or nearly normal? Well, we have a maximum score on a test, right? 100%. And so that limits the size of your data values. Now, if it's easy, that means that there's probably going to be a lot of high scores, right? And they're going to be near that 100. Versus there's going to be fewer lower scores. And so on our distribution, this is 5.1, example 1, part A. So if we're looking at our distribution, we're looking that there's probably going to be more high scores and a few low scores. So we're probably looking at something like this that will be left skewed. It's not going to be normal. So not normal, and instead it'll be left skewed. Because if it's an easy test, we're going to expect more of the high values. The second question says foot lengths, so foot lengths of a random sample of adult women. Foot lengths, so the length of their feet. So that's going to be a human trait. It's determined by the genetic and environmental factors. So we're going to expect that a lot of them are going to be near the mean. And so we're expecting more of that near the center part. There'll be a few that are longer and a few that are smaller, but we're going to think that this is going to be normal. We would expect it to be most of them in the middle, a few smaller, and a few larger, because they're pretty common in the sizes, right? You see that in the store when you go look at shoes. All right, what about IQ scores of adults? Well, those are a standard test, and the scores tend to center around 100. The scores can become less common farther from the mean of 100, but they are a measure of intelligence, and that's a trait determined by genetic and environmental factors. So we think that it is also going to be normal. So again, we'll have the big cluster, and then we'll have some here and we'll have some there. All right, so next we're going to talk about areas of relative frequencies. So we are going to look at some questions and we're going to figure some stuff out based on that. All right, so here's our question. We're going to consider the graph of the normal distribution, which gives relative frequencies in a distribution of men's heights. The distribution has a mean of 69.6 inches and a standard deviation of 2.8 inches. What is the total area under the curve? Well, if we're talking about the total area under the curve, what did we just say would be the deal? We just talked about that the total area under the curve must be equal to 1. So, example 2, part A is going to be 1. It has to be equal to 1. You could also say it's 100% if you want to talk about percentages versus decimals. So, it's going to be equal to 1. That's the total area under the curve. Always going to be that. Now we want to estimate, using the area, the relative frequency of values less than 67 inches. All right, so I have some pre-printed graphs here because I wanted to make sure that we could do these a little bit easier. I'm also going to use pencil, and hopefully it'll show up okay, just because it'll make a little bit it'll make it a little bit easier to draw. All right, so this is the graph of our data, all right, with the height of, because we're looking at men's heights, right? Our mean is 69.6, so I'm going to make a mark here at 69.6. That is, move that in just a little bit. And I guess I could write those numbers. That I can do in pen. Let's make that pop. So 69.6 is our mean, okay? Right, mean? Yes. And if it's a standard, a normal distribution, it's also the same as our median and our mode, right? 69.6. And we've got a standard deviation of 2.8. So at this point, that part doesn't matter a whole bunch. So we want to find out what is the, we're going to estimate the area of the relative frequency values that are less than 67. So let's go make a mark at 67. And so we're looking at, if this is 60, oh, I guess I should have put it more in the middle. Let me put it in the middle. So 67. We want the less than part of 67, right? So we're talking about this part right here, okay? And here is our center, our median, our mean. All right, so understand that when we're looking at the total area under the curve, if this is a normal distribution, it's going to mirror itself, right? So that means half of our data is above it and half of our data is below it. So that means that if the total area is 100%, then part of our area is going to be 50%, this part here, right? This is 50% up there, this is 50% down here. So of this entire part right here, we have this chunk and we have that chunk. We want to know what, and we're just estimating. We'll learn in the next section how to pinpoint it, but right now we're just doing an estimation so you get an idea. So I could say if this is 50%, this one is less than this one. So if I was looking at, well, if they were equal, it'd be about 25 and 25, right? But I'm saying that they are not equal. So because this one has a little more, I'm going to say this is about 30% and this one is about 20%. Okay, so I'm saying this part is 20%. So for part B, I'm going to say the area less than 67 is going to be 27% or 20%. Okay? All right, now let's go look at our next question. We want to estimate the relative frequency of values greater than 67. So greater than 67, if our 67 we know is, we said this part between this and the mean is going to be 30%. That's what we estimated. Now we also talked about that above that mean we have 50% of our data, right? So what I can say then is for part C, it's going to be 30% plus the 50%. So it's going to be this whole area and this whole area here. All of this area is going to add up to be a total of 80%. Okay? So again, we're estimating. Half is always going to be 50%. We've already claimed this is 20, this is 30. We just add those two together. All right. Our next part is part D. And on part D, it says estimate the relative frequency of the values between 67 and 70 inches. So it's between 67 and 70. All right, I'm going to go down here to, let's pull out green. All right, so between 67 and 70. So now what I want, this is 70 right here, and I want that area between 67 and 70. So I'm looking at this area right in here plus this area. So the parts where I've now marked it in green. So between 67 and 70, well, I've claimed this is 30, and I'm doing an estimate, right? But I got to go a little bit more. I'm just going to say that this area here, I'm going to say is 5% in that area. Well, that's going to be 30% plus 5% will get me 35%. Because I'm just estimating. I'm not finding the exact value. I'm going to say, well, that's about 5%. It's tall because it's, near the mean, the median, whichever way you want to look at that. All right, and then part E says estimate the relative frequency of values that are greater than 70. So I want the greater than 70 part. So that means we're going from 70 and up. So let's pull another color. Let's see if this purple will make a difference. So I'm looking at now from this 70 point, and we're looking at above the 70. So 70 and above. Well, we talked about that from 69.6 up, that's 50%, right? So if this is 50%, and we've already said this is about 5%, then I can take my 50 minus 5 and get 45%. Okay? Hopefully that's making sense to you. I could have redrawn the entire parts on different graphs, but I thought, well, we've kind of got this happening. So 20% happening. We've got 30% in these sections. We've figured out 5 there. And this over here is our 45. And you're just guesstimating. It's just like, okay, so that looks a little bit more than that. And so hopefully that makes sense to you. All right. Our last question is, does it make sense? So the distribution of the Chromebook sales data over the last year is not normal because it has 2 modes corresponding to the holiday season and back to school season. So Chromebook sales is not normal. It has 2 modes corresponding to holiday season and back to school season. Does that make sense? It says it's not normal because it has 2 modes. Well, that's true. And I would say that it makes sense because holidays and back to school season is typically when we would see people buying computers. So those two modes make sense in my mind. But the fact that they said it's not normal, it has two modes, that is a true statement. So for example 3, it's going to make sense. And that's because a normal distribution can only have one mode. All right, so that is what is normal. We'll go a little bit deeper into what's going on underneath the normal distribution in our next lesson.